Hello and welcome. My name is Roman Crimmy. Joined with me is Cole Bennett, Elliot de Hollander, Gabriel Stevens. Today we'll be presenting our research on the aerodynamics of a ballistic object. The study of aerodynamics in projectile objects has countless applications in the real world. For our purposes, we'll be focusing our studies towards the drag forces imposed onto blunt ballistic objects. Some prior experimentation has been completed with some designs that we tested, including the United States Army. Our experiment focuses on 5 different designs of blunt ballistic objects, each with defining design characteristics. The purpose of our experiment is to experimentally analyze the drag force imposed by each design and to see which one creates less drag.
The planner is fairly simple, with the design and calculations being in a 2-week period, the analysis of the calculations and experimentation being in a 2-week period, the analysis of the experimentation and comparison of the experimental to the theoretical, and then finally completing the final report. Fairly straightforward were the first 3 weeks. The experimentation section did tend to drag on, and the final report was banged out fairly quickly. The budget for this experiment was initially reported to be zero due to the fact that everything was 3D printed and all experiments were held on Clarkson campus, so nothing had to be paid for. After further analysis of what we needed for the experiment, it was concluded that it cost roughly $7.79 to complete the experiment, which in this case would be null. For the procedure, you must first perform calibration of the wind tunnel as reported in the technical document using NIMAX software. Then remove acrylic panel on the side of the test chamber and fasten the sting mount onto the force balance. Third, make sure the sting is at 0 degrees relative to the incoming airstream. Replace acrylic panel and make sure that all clamps are set. 4, set the motor control at 3 Hz and turn the tunnel on. 5, at each airspeed, record the static pressure from the 20th channel on the manometer. Incrementally increase the frequency of the motor by 0.5 Hz. 6, record 10 force data points for each frequency because the natural noise that is produced from the DAQ to software. And 7, repeat step 6 until a maximum frequency of 6 Hz is achieved.
So the equipment used for the experiment was a Model 402B, one engineering laboratory design wind tunnel, 2 full bridge thin beam load cells, model LCL 010, and pictured to the right there, the 20 channel manometer. We used the 20th channel for static pressure.
Pictured on the slide here are the 3 equations that we used after experimentally collecting the data from the wind tunnel. The first equation that we used was to calculate velocity, which accounts for the density of water inside the manometer, as well as gravity and the height difference on the manometer. And the denominator of the fraction is the density of air. And from that, we were able to calculate the Reynolds number, which accounts the density of the air as well as the characteristic diameter inside the wind tunnel, as well as the dynamic viscosity. With that, we can then calculate the coefficient of drag, which is a factor of the force of drag, which accounts for the air density, as well as the velocity and the area. Pictured on the graph here is the force versus velocity plot that we generated from the data in the wind tunnel. On the x-axis is velocity, the y-axis is the force. As you can see from the figure, it is an exponential relationship between the force of drag as well as the velocity. What was surprising that we noticed was that the dimple design had a lower drag throughout most of the curve here, and that the rifle design had a higher drag initially, but dropped off around 40 meters per second. The second figure that we obtained through the data analysis is the coefficient of drag versus Reynolds number. On the x-axis is the Reynolds number that we calculated, which ranged from around 50,000 to just shy of 90,000. And on the y-axis is the coefficient of drag. As you can see from the graph itself, you can see the inverse squared relationship of the coefficient of drag, and at low Reynolds numbers, the drag decreases significantly.
Here you can see a summary of our statistics. There's the average, the standard deviation, the variance, and the median for each of the designs. And some of the possible sources of error include noisy data that we got from the force balance, the sting and the mount in the wind tunnel contributing to excessive drag, and some deformities that we had in our 3D printed models, like Z-seam axis and other things generating additional turbulence. Some of the things that made this project take a little longer than expected were mounting holes were too small in 3 of the designs, so we had to reprint. You can see the mounting hole pictured to the left on the screen. Completing accurate CFD analysis took longer than expected, and when we compiled all our data, the drag coefficient numbers were unreasonably high, but the trends that we saw were typical for coefficient of drag versus Reynolds number.